Welcome to part 3 of the chemistry unit 2 Edexcel IAS specification revision. So, in today's video, we will be covering intermolecular forces. The previous video was energetics, a bit of energetics. But yeah, so let's begin with 7.1. Understand the nature of the following intermolecular forces. Okay, so when we talk about intermolecular forces, we have three main types of intermolecular forces, okay? One is going to be van der Waal, sorry, let me just write it like van der Waal forces. The second one is going to be a permanent dipole, permanent dipole, and lastly we will have hydrogen bonds, okay? You've probably heard about most of these, but for those who maybe you've not heard these specific terms, but another word for van der Waals is London forces. And another word for van der Waals again is going to be an instantaneous induced dipole. Okay, instantaneous dipole, induced dipole. Okay. Now, the reason I like the third definition the best is because it creates the best understanding for what van der Waals. Basically, they all mean the same thing, but to me, the last one creates the best understanding of the term, okay? Because we can just look at the term itself. An instantaneous dipole is going to be a dipole with a positive and a negative, and then a dipole next to it. Because of this negative, electrons will be repelled away to this side, so become negative here. So the negative electrons will move to the other side, and this side will be positive. So this is an instantaneous dipole, and this is an induced dipole, okay? That's essentially what van der Waals / London forces / instantaneous dipole induced dipole means, okay? Now, this is so we can just, let me just write like this. This is going to be the weakest bonds, okay? Weakest type of intermolecular force. Weakest type of intermolecular force. So yes, moreover, we need to know that the larger the compound size, the greater the strength, okay? Now, obviously, we don't talk about compound size. Instead, we talk about the relative molecular mass of the compound, okay? So the greater this, the greater the strength, okay? It's important to note that. For example, let's look at an example right now. Alkanes. When we talk about alkanes, we know that let's look at C6H14 will have a greater boiling point than CH4, than methane. Methane is a gas at room temperature. Hexane is a liquid at room temperature, okay? This is because of the greater strength of the van der Waals forces. They both have the exact same type of bonds. It's just that the bigger one has more relative molecular mass, hence more strength of intermolecular force, okay? We got that done there then. So that is for the first one. Now let's talk about permanent dipole, okay? A permanent dipole is going to be, it's a type of intermolecular forces that acts between polar bonds, okay? Polar compounds, okay? Let's look at HCl as an example. HCl, let me draw that better. HCl. The H will be delta positive and the Cl will be delta negative. Essentially, another HCl comes here, and this is delta positive and this is delta negative. These are two instantaneous dipoles, okay? There will be a bond between this delta negative and delta positive, and essentially that's how it will form throughout, okay? This is basically what a permanent dipole is, okay? I don't know why I said instantaneous dipole. But next part. So this only happens in polar compounds, and they work in a lattice structure. So this structure here is known as a lattice structure, okay? But Polar bonds work in difference of electronegativity. There is something that I want you guys to search up if you're studying this. An electronegativity graph. Okay. You will see that. So you will get a graph of the periodic table. Okay. That is not how the periodic table looks like, but sure. There will be an arrow like this, and here you'll find fluorine here. Fluorine is the most electronegative compound in the periodic table. Okay. Yeah, but just do your research on that and you'll see how effective it is reading all of that stuff, okay? Lastly, we'd like to talk about hydrogen bonds. Hydrogen bonds, we will do it on this page, okay? It is so hydrogen bonds, this is the strongest type of intermolecular force, and essentially it's in the name itself. A hydrogen bond is going to be the bond between a hydrogen atom and three of the most electronegative atoms, which are nitrogen, oxygen, and fluorine. Fluorine we talked about is the most electronegative. So hydrogen will form hydrogen bonds with these, and it is, yeah. Let's look at it in detail, okay? Let me just take this first. Understand interactions in molecules such as H2O, NH3, and HF, okay, which give rise to hydrogen bonding. We just talked about these actually. Let's just cover it though. In H2O, and by the way, this works with NH3 and HF as well, so we'll only be looking at H2O. Yeah, so if we have O, H, H, the H will be delta positive, the H's, and the oxygen will be delta negative. Another hydrogen water molecule comes here, and this is delta positive, delta negative, delta positive, okay? So there will be a hydrogen bond formed between these two, and this angle will be 180 degrees, okay? The reason I talked about this angle is because various exams have asked this question on what is this angle, okay? So it's important to note what that angle is, okay? But yeah, again, this bending is due to, the free electrons over there. But yeah, that's previous stuff that we have done. Okay, that works for NH3 and HF, the same concept but different forms, okay? We can take that. So next part, understand the following anomalous properties of water resulting from hydrogen bonding, and then these two properties it's given, okay? Let's look at what these are. So the anomalies in water are due to two reasons, okay? So ice, although is a solid, has a lower density than water, okay, which is a liquid, obviously, okay? Why is this? Why is this the case? Yeah, so in ice, the hydrogen bonds form a stable structure, okay, between each other. So it will form, if I can draw it in a better way, it will, yeah, I got it, okay. So let me represent it using these dots, okay? So this is going to be a water molecule. This is going to be another water molecule, and there's going to be hydrogen bonds between it. This is going to be another water molecule with hydrogen bonds between it. But essentially, you can see a pattern starting to form, You can see that there is going to be specific gaps over here, as shown. There's going to be a fixed structure here. So this is an ice. Oops. I don't know why it's coming like that. 1 second. This is ice, okay? Now, if we look at it in water, it's going to look the same, just with some differences, okay? You can just select this, and water is going to be more compact, okay? So similarly, hydrogen bonds are going to exist between molecules, but it's going to be more compact, hence it is going to be more dense then ice. Ice is going to be less dense. So that's the reason why ice floats in water, okay? But yeah, so water has a simple molecular structure. This is the second anomaly, okay? It has a simple molecular structure, but has an unusually high boiling point for that size of molecule, okay? The relative molecular mass of water, of H2O, is going to be 18. For this size, you would expect a compound to be at gaseous state, right? But water is not at gaseous state. Let's look at methane, for example. Methane is CH4, that is 16, but compared to 18, obviously 16 is less. But methane is a liquid, a gas, Water is a liquid because you will form hydrogen bonds here, but you won't form hydrogen bonds here. That is why in water, you will get a greater boiling point, okay? That's why the boiling point of water is going to be 100 degrees Celsius, okay? Pure water. But yeah, so we can take those two down. Be able to predict the presence of hydrogen bonding in molecules analogous to those mentioned in 7.2. Okay, so 7.2 have been given these, okay, these three compounds. Let's specifically look at page F. So if you have a hydrogen halide, those are HF. So hydrogen halide, we have HF, HCl, HBr, and HI, okay? You draw a graph of these three with the boiling points, boiling temperatures. Yeah, and let's say here's HF, HCl, HBr, and HI, okay? Hydrogen iodide, okay? HI will be the highest, and HCl will drop, and then HBr and HI, okay? So it's going to look like this. Why is this greater than all the other three? Well, that's because one, HI is the only one that has hydrogen bonds between molecules. And why is there an increase here? We're also supposed to know that. It's because, like we talked about, you have a greater size, so you have a greater relative molecular mass, you'll have a greater strength of the weak van der Waals forces between the molecules. So these will have stronger weak van der Waals forces compared to HBr and HCl. Hence, it's going to have a greater boiling temperature, okay? Not as much as HF because, this is going to be a HF. I don't know why I wrote HI, HF. Not as much as HF, these three, but yeah, still, you will see a general progression, okay? Yes, we can take that. Understand in terms of intermolecular forces, physical properties shown by substances, including trends in boiling temperature of alkanes with increasing chain length. We talked about this already, like we talked about C6H14 and CH4. That's hexane and methane. We talked about those already. The effects of branching. Yeah, branching is something we have not talked about yet. Okay. So, with branching, there is going to be a slight change over here, okay? Van der Waals forces act between alkane chains, right? And they're affected by chain length, like we've seen with hexane and methane. But they also act with branching, okay? As chain length increases, your relative molecular mass will increase. So that will increase. So it's a higher, stronger, so let me just try this, higher strength of intermolecular forces. That's for the first one. For the second one, branching of alkanes weakens the weak van der Waals forces because there's less, they're able to pack together less. What do we mean by this? If you have a straight chain, another straight chain can go over it and it's very tightly packed. But if you have a branched chain now, you cannot look at this. In the same space as this, we can probably add another two. And we are only getting 3 alkanes here, while here we're getting a lot, So the more branched it is, the lower the strength, okay, of the intermolecular weak van der Waals forces. Yeah. So yeah, that is that. Trends in boiling temperature of hydrogen halides. We've talked about this just now. But yeah, we can take this then. Next part, understanding factors that influence choice of solvents. Okay, when you're looking at a solvent, you're going to look at whether or not it can dissolve that specific solute, okay? Um, just know this simple rule. If you want to dissolve polar solvents, use a polar solutes, use a polar solvent, okay? And if you want to do a non-polar, if you want to dissolve a non-polar solute, use a non-polar, non-polar solvent. Majority of the time, you'll be tested on this first one. So let's look at it a bit in detail. When you dissolve, okay, so when you are dissolving something, some ionic compound, what happens is they will ask you to draw a specific diagram, okay? Let's say you have NaCl salt, okay? And you want to dissolve this in H2O. They'll ask you to draw this. What do? You draw the sodium cation, and you draw the chloride anion, and then you draw your H2O around it, okay? O, H, H, O, H, H. Here, all around, okay? If that makes sense, okay? H, 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 H. Here, it'll be slightly different. But yeah, essentially, this is how it's going to look like. Sorry, 1 second. Yes, okay. Now, you might be asking, why is the hydrogen here? Actually, you might not be asking that, but that's because here in this first case, oxygen is delta negative, and negative attracts the positive, right? And here in the second case, it's hydrogen is positive, and the chlorine is negative, so these will attract each other, okay? So this is the diagram that you're going to draw if they ask you to do that, okay? But essentially, that's everything about solvents, but yeah. So in the next, so we don't cover further suggested practicals in the Unit 2 videos. We cover those in the Unit 3 videos. But yeah, that's why we skipped the previous ones as well, like these ones, and the core practicals as well. These will be covered in the Unit 3 chemistry videos, okay? In the next videos, we'll be looking at redox. Yeah, we'll be looking at redox chemistry. We'll finish that, and then in the video after that, we'll be looking at the elements of groups 1 and 2, okay?